Öncelikle halen biraz süresi uzatıldı ödevin gerçi ama bir birinci ödeve birkaç gün daha verdik yanlış hatırlamıyorsam. Ama bu ikinci ödevin yayınlanmasında önüne geçmedi tabii ki. Bununla alakalı videosunu paylaştım. Sadece hızlıca değinmek gerekirse aslında birinci ödevde yaptığınız veya ele aldığınız sistemi ikinci ödevde devam ettiriyorsunuz. E, Onun üzerine bu defa PID kontrolöre geçiyoruz. PID kontrolörü tanımlıyorsunuz. Ve yine aslında benzer şeyler isteniyor. İşte kapalı çevrim için, kontrolörler için hem TF hem ZPK formlarını yazın. Basamak yanıtları, step info, işte kutup sıfır haritaları vesaire gibi dokümantasyon kısımlarını ekleyin muhakkak denilmiş. Herhangi bir değişiklik yapılmamış sistemde. Sadece tüm PID kontrolörlerini e, işte istenenleri veren tüm PID kontrolörleri ifade ediniz denmiş. Burada Efes'in parametrik olacağını unutmayın. Nasıl yapılacağı aslında çok temel adımlarla belli. Sadece bir parametreyi seçeceksiniz. Fazladan parametre, o parametreye göre tüm PID kontrolörüyle ifade edeceksiniz birinci soruda. İkinci soruda şöyle bir durum var. Biz baskın kutup atama kullanıyoruz. Burada da yine baskın kutup atama ile alakalı birkaç durum var. Birincisi rezidü kutupları üzerinden maksimum ne kadar uzağa gönderebiliyoruz? İşte diyelim ki e, şimdi şeyleri hatırlamıyorum değerleri ama diyelim ki reel kısmımız -2 dominant kısımda. -2'nin kaç katı uzağa yani kaç katına atayabiliyoruz? Direkt kaç katına gibi düşünürseniz yeterli. Yani -2 ise baskın en yakını da -20 ise dominant faktör 10'dur. Yani bunu bu şekilde hesaplayın. Bu rezidü polinomu için maksimum kaçtır? Yani rezidü polinomunun kutupları hepsi birden en uzağa kaç katına atılabilir reel kısmının? Ee, Sıfırlar için nedir? Bu ikisinden farklı değerler gelecek ve bu ikisini birden maksimum yapan değer nedir gibi bir sorumuz var Q2'de. Ee, Yani bir rezidü kutuplarını öteye atacaksınız. Bir sıfırlarını atacaksınız. Bir de hepsini birlikte uzağa attığınızda kaç olabilecek? Q2'de bunu gösteriyor. Tabii kaç olabilecek veya kaçtır sorusu aslında tüm tasarımı istiyor. Artık burada seçmiş oluyorsunuz şu kadar kat diye o kadar kat olduğu için de tüm PID katsayılarını hesaplayıp kapalı çevrimi bulup basamak yanıtlarını bulup vesaire hesabını yapıyorsunuz. Q3'te de sorunun soruş şekline tamamen dikkat edin. Bu aslında çok klasik bir şey söylemeye çalışıyor. Ben doğrudan söylersem cevabı söylemiş olurum. O yüzden sorunun söylediği şeyi tam anlamıyla anlamanız lazım. PID'yi nasıl e, değiştirir, düzeltir veya PID'ye nasıl bir şey yaparız ki sıfırların kötü etkisinden kurtuluruz gibi bir soru. Bu soruyu kendi içinde anlamanız gerekiyor. Bu aslında size bir şeye işaret ediyor. Son soruda model matching controller ki bu hafta zaten işleyeceğimiz bir konu olacak o. Son soru zaten çok problem değil. Açıkçası birinci ödeve göre hatta ikinci ödev belki daha basit kaçabilir. Birinci ödevi bitirir bitirmez ikiye de bir an önce özellikle sınavdan önce bakmanızda fayda var diyelim. E, Derse de geçmeden önce yani PDF yükleyeceksiniz, raporlarınız düzgün olsun vesaire bunları söylemiş olayım. Ödev bir ödev 2 bu şekilde aslında. Ödev 1'in süresi tamamlanmak üzere. Ödev 2'yi yeni yayınladık fakat benim tavsiyem sınavdan önce tabii ki ödev 2'yi yapmış olmanız. Bu hem sınava çalışmış olmanız anlamına gelecektir. Hem de ödev yapmış olursunuz. Çünkü ondan sonra tarihi de çok uzağa değil 20'sine kadar verdik. Bu kısımlar önemli. Bir de bir anonsum daha var aslında. O da normalde haftaya tatil haftası, ara tatil haftası malum. Ve ara tatil haftasında normalde biz soru çözümü yaparız. Ben size link paylaşacağım. Daha önceki senelerden çözdüğüm hem İngilizce hem Türkçe soruları size yönlendireceğim. PDF'leri de yönlendireceğim. Sıfırdan bir bu sene için gerek gözükmüyor gibi. Çünkü aslında her dönem aynı sorular üzerinden sohbet ediyoruz. Birazcık nüfusun kalabalık olmayışıyla alakalı da bu şekilde bir çözüme gideceğim. Bayağı da bir şey var aslında orada hatırladığım kadarıyla. Yani 4 saatlik falan bir video olması lazım. Linkleri zaten Discord üzerinden paylaşırım. Oradan bakarsınız. Soru da var. Komplesi de var playlist olarak. Dolayısıyla sınava hazırlık şeklinde de o kısımları incelersiniz. Tabii yine genel anlamda bana sormak istediğiniz şeyler olursa Discord üzerinden yine ulaşabilirsiniz. Evet. Bunu da anlattığımıza göre dersimize geçebiliriz. Tabii bu anonsları bir de İngilizce tekrar etmekte sanırım fayda olacak. Önce tabii bir daha ödevi açalım şuradan. So let me repeat the Turkish stuff again for non-native speakers. Of course, I have announced homework 2, although homework 1 has some due still, maybe 1 day or 2 days, I don't remember. But yeah, in homework 2, it's kind of a continuation. You are just going to use the same system, same specifications, and all the request is almost the same because you will again provide the controller and closed loop transfer function and ZPK forms in your report. Also, when you have a design, please provide the step response, step info, pole zero map, everything that will kind of recap the whole thing and verify the results. If you have a controller, you have to test it and verify the results. So we have, again, the same heating system here, again, the same desired specifications. But now we are interested in all the PID controllers that regulate the heat as desired. So you will come up with a PID controller that is kind of doing the purpose here. But keep in mind that your controller will be a parametric one. You will have a free parameter, and all the coefficients will be in terms of that parameter, preferably controller parameter, like KP, KD, KI, choose one of them. And you can just express the whole transfer function, the controller, in terms of that free parameter. So you're basically asked to provide the PID controller that satisfies this. Of course, I have to also remind you that by defining all the PID controllers, you should also keep track of the stability of the residue polynomial. So that's also interesting and important. So not any kind of parameter, but maybe the parameter might have an interval. So that's also important. If we ask about a of all the PID controllers, of course, we mean that the closed loop should also be stable. So the dominant poles hopefully should be 10 seconds and 10% overshoot, but they should also at least be stable. We cannot assure how dominant they will be. So you will provide a parametric FS, but the parameter might have an interval. So the next question is, again, about the fact that we have a family of PID controllers available. What is the maximum dominance factor for the residue polynomial? Because we will have the residue polynomial, we will have the zero polynomial, and during the dominant pole placement strategy, what we are trying to do is we're trying to assign 2 dominant poles, and we want to push all the poles and the zeros other than these 2 dominant poles as far as to the left as possible. So basically, it is important to work out this problem. And here we have 2 different issues. One of them is the residue polynomial. There will be some residue poles to push away. So how far can we push away these poles? And then there's this problem about zeros, because the PID adds 2 zeros. We are trying to push them away too. So how far can get the zeros be pushed? How far can we push the residue poles? These are 2 separate questions. And then as a third one, what is the overall maximum dominance factor? Means that we are trying to push everything away. How far away can we push the zeros and the poles? So you have a separate issue, raise the poles, the zeros, and then combined. And the dominance factor is basically the following. If you have the real part of the dominant poles -2, if you can push something to -20, this is 10 times. So the dominance factor is 10 times for -20 and -2. So between -20 and -2, the dominance factor is 10. So just get the ratio of the real parts. So basically that's what I'm trying to say. But of course, the closest one should be as far away as possible, if that makes sense. So define all the PID controllers. What is the maximum dominance factor also means that you have a dominance factor. You will get the parameter value, so you will have a PID controller that pushes away everything as far as possible. So in Q2, you should end up in a design, and then you should verify the design with adding some transfer functions, APK forms of the controller, the closed loop, then some step responses. You should provide results here. Just don't only give the dominance factor. If you have a dominance factor, you have a controller, you have to plug it in and try to see how it works, if it works, and why basically it works. And then there's Q3, which is a very specific question. Its phrasing is very specific. It tries to hint you to something that is quite important. And it goes as following. Rearrange your PID controller in order to get rid of the adverse effects of the controller, zeros, and maximize the dominance factor of the desired poles. So basically, this is not a redesign question. You don't have to come up everything from scratch. This is just a rearrangement. And if you come up with this rearrangement, you will just provide the results and compare it to Q2. So Q2 has a design result. Q3 will also have a design result, and probably with one sentence, you should explain the difference or the advantages or disadvantages it may have. And the last question is pretty straightforward. Design a model matching controller. And today's topic, fortunately, is about PID controller and model matching controller. So it's basically aimed to this homework. And as I suggested, you should actually try to solve this homework before your midterm exam, because next week will be our week off, and there will be no lesson, no laboratory session whatsoever. So you would have time during your studies for your midterm exam. You should basically try to finish this. I would suggest you to do that, because this would also mean that you would work or exercise for your midterm exam, and you would also get rid of the problem of having it homework. So yeah, you should basically address this homework as soon as possible. And there's another issue that I want to touch base on. That is, we won't have a laboratory session next week. And traditionally, what we do is we have a midterm session where I have some questions and I solve them. But during the pandemic and during the last semesters, I have pretty much a good playlist available. And of course, if I would have a midterm session, I would just go ahead and solve the same questions over and over again, because time and stuff. So basically, I will give link to 2 different playlists. One will be in Turkish, one will be in English. So you can just watch them over and over again, and you will also have the PDF. So basically, I will give you the playlist of the midterm session. There will be no midterm session, but if you are stuck with a question, or if you want to ask something, feel free to write from Discord. Maybe someone helps out, even if I'm not available, or I myself might help you out. So if you have any questions for your midterm exercises, feel free to ask. So basically, I'm going to upload videos, or I have just uploaded the videos. I will give you a link for each question. You can then have the videos, just watch them and try to solve it on your own. If you have any questions, just then feel free to ask me from Discord, of course. So let's move on to our today's lecture. Now we have a transfer function as usual, and there are some specifications: 10% overshoot, 2 seconds settling time. So let me first define the transfer function here. It's 1 divided by 1.225.01. So let me also define the symbolic version here. There we go. Then we have settling time, I guess 2 seconds. And overshoot of 10%. So basically, we are going to design a PID controller using the tabulation methods. We have talked about the tabulation method last week. Then we are going to propose the PID controller, and then we are going to propose a controller. Now, if you see a set of questions that looks like this, you should be terrified, because we are using the most known PID controller, and then we are proposing it ourselves, even though we have a tabulation method available. So, and then we again scratch the PID part and propose a controller. So it's there's something going on here, basically. You should get the hint from this, because if it would have been the inverse order, if we would have proposed the controller and then proposed the PID controller and then maybe designed the PID controller using the tabulation method, that would mean something else. That would mean that, of course, we are trying to have some brainstorming going on, and then we're just going to design it. But here it's inverse. So it means that during the design, we will hit something, and then we will see and try to solve that maybe, and then come up with an even better solution, hopefully. So this is not an ordinary task here to do. But let's see. So if we have overshoot, these examples are sample in both playlists. Example are the same in both playlists. Yeah, of course. In the previous semester, I guess, we had a parallel classroom where one of them was Turkish, one of them was English, and I was just solving both questions. And but the quality may change, by the way. The English one could be a higher definition one, because I used a tablet there, as far as I remember, and the other one was a classroom recording. So maybe you want to check both of them out. I don't know, but yeah, one of them was an iPad screen recording, the other one was a classroom recording, but the questions are available in a PDF with the solutions and everything, and there's just the explanation as additional video. So there's no difference at all. If we have an overshoot of 10%, the immediate thing that pops up is to try to calculate the zeta here. And let me again warn you for your midterm exam, because most of the time we use the MATLAB commands window, we use the MATLAB scripts. I would highly recommend you to pick your calculator and try to solve these types of things with pen and paper, because you will have pen and paper available and your calculator available to you in the midterm exam. There will be no MATLAB computer whatsoever available to you. So we're used to MATLAB, but maybe for a classical exam, we should try to use pen and paper and calculator. Just a reminder. So, and the reason why I actually said this is because of this log formula here. If you use log on its own, well, you might have an issue in the exam, because this is log base E. So you don't use E if you are in MATLAB. So this is log n, or natural log, ln, but we write it as log. And if you want to use log base 2, log base 10, you have to provide the extra number here. So be aware of that. So log overshoot divided by square root of pi squared plus log overshoot squared. There we go. And let's check out what zeta is, because yeah, it should be 0.5912. Yeah. And we can then come up with omega n, which should be 4 divided by ts times zeta. This is the inverse formula, of course. It is basically ts is equal to 4 divided by zeta times omega n, but I'm just replacing ts and omega n because I need omega n. So let's define our controller, kd, kp, ki. These are all real values. And I'm not using k, z1, z2. Avoid this stuff, because I'm using the algebraic method. In the algebraic method, coefficients are very useful, and poles and zeros are very problematic. So I would just recommend you to use KD, KP, KI. And in the residue polynomial, in a moment, we'll see I'm going to do the same. KD, you can write this as KD S squared plus KP times S plus KI, the whole thing divided by S. KI divided by S, or KD plus KP, KD times S plus KP plus KI divided by S, whichever you prefer. I prefer this one here. So due to the structure of our connection, we have FSS-GSS divided by 1 plus FSS-GSS. This is the closed loop transfer function. Now, we're interested in the zero polynomial and the characteristic polynomial. Using num then, we get the data. Now, I have a second order transfer function here. The PID will add just 1. Then we will have a third order closed loop, which means that we have 2 poles available because zeta and omega are known. We need just 1 extra residue polynomial. Let's call it, I don't know, A. And let's choose it to be real. So PES should be S plus A. The problem should be coefs of PCS should be equal to coefs of PDS times PS, all the coefficients. Of course, we didn't write down what PDS is. S squared plus 2 times zeta times omega n times S plus omega n squared. So let's see what the problem looks like. There we go. Now, at first sight, we can see we have a slight issue. And the issue is being that our first equation is 100 equals 1, which is, of course, not true, which is a false identity. Therefore, we are not able to solve this set of equations if it's going to be like this. But it is also obvious that we don't really have to have 100 here, because we can normalize the left-hand side of this set of equations where everything can be divided into 100. And then we would have 1 equals 1, and then KD plus 0.2 equals A plus 4, and so on and so forth. So it means that we have a little step here that we have to carry out. Maybe we call it pol. We take the characteristic polynomial coefficients here. You could also do it like coef. And then we normalize it, coef divided by coef, the first elements. So let me just demonstrate to you what it is going to do. This is the vector. This is coef 1. If I divide coef divided by coef 1 and store it back in coef, I will store this in coef. So it's going to be normalized. And from that on, I can just say, okay, use this coef instead of that. Sometimes this is necessary. There we go. Now you can see that the trivial equation is actually a necessity. You have to have the highest order term with coefficient 1 if you are going to use this. Another way would be to include 100 times PDS times PES, but I don't like to use that way. Maybe if you're in an exam, you might go for that one, because that might be a bit easier to do. But theoretically, I don't like that approach. I like to normalize PCS. So now we have KD, KP, and KI. And we have 3 equations. It means that we have 4 unknowns and 3 equations. What we can do now is to choose one parameter like Ki and solve everything in terms of Ki. So that's exactly what we are going to do. We have one coefficient that we can use here, and we are going to just choose Ki, for example, and try to solve the whole set of equations in terms of Ki. So let's call it solve. And let's take the problem, but we want to solve KD, KP, and A. We don't provide KI, so the solution will have KI as the free parameter. So sol.KD is in terms of KI, sol.KP is in terms of KI, and sol.A should be in terms of KI. Now, for stability, of course, I can see that sol that A is important for that, and I can see if Ki is positive, A will be positive, and if A is positive, the residue polynomial will be positive or stable. So therefore, the closed loop will be stable. So having positive Ki values is sufficient for this system. This might not be always the case. You might want to try look at your residue polynomial and maybe use the root tabulation, maybe Root-Hurwitz criterion, whatever. You might want to look for some stability evaluation there. But here I can immediately see, because it's the first order one, if A is positive, S will be minus A. So if A is positive, this will be negative, so it will be stable. Therefore, I can go ahead and choose a Ki vector here. And let's start from 0.1 with 0.1 steps up to point, let's say 5. So then we are going to define a table. And the reason for that is we are using tabulation. Now we will have length Ki vec rows, but how many columns do we need? Let's see. We have settling time, we have overshoot, we have KD, KP, KI. Let's have 5 for the moment. So 5. Let's now open up a for loop. I length Ki vec. Ki val is Ki vec ith element. So now actually we can now solve what KD val is, for example, double subs sol.kd had our solution, and our Ki value is going to be Ki val. So into sol.kd, because the solution is here, we're just substituting Ki value into Ki. So we're going to repeat that for Kp, I guess. And this is going to be Kp val. Now, at this point, we have what we want. We have the PID controller, actually. We can just define it. And it would go like this: KD val, KP val, and Ki val, comma 1, 0, because we have an integrator. Then we can define the closed loop here. Fs times Gs, comma 1. Now we can use step info in order to acquire the time domain characteristics. And let's call it TSE, info.settling time. OSE for overshoot. So what we can do is we can save these values into the ith row. We set that KD val, KP val, Ki val, and then TS and OS should be the values stored in the table. There we go. Now, KD val, KP val, Ki val, TSE, and overshoot. Now, we have talked about the tabulation last week, but let me just remind you that we are trying to match the settling time and the overshoot. So this is kind of a multi-objective optimization. Therefore, we have to combine them in some sort in order to come up with the optimal controller that we're after. And since we have the settling time and the overshoot, what we can do is we can just convert them into relative errors and then combine them equally, and then we will have just one metric or one objective that should be minimized. So by that I mean the following: we can use the settling time error, for example, like the difference between the settling time that is the result and the settling time that is the specification. normalize it with TS. And if you want to have it as percentage, you might also multiply it with 100. So we can do the same for overshoot E, and then overshoot. As far as I remember, I should divide by 100 if I'm using overshoot, or OS times 100. So this would be the relative error 2. I would combine them equally. You can change this. If you value the settling time more, you can increase its weight here. If you value the overshoot more, you can increase that weight in order to come up with a better solution towards the overshoot or the settling time more equally. So therefore, we should increase the column by 1. And this is basically our objective or error or metric. So let us basically, let me see. Maybe we should do this up to 100 for now. And before I do this, what I can do is I can plot, actually create a little plot here in order to keep track of the optimal solution. So we can plot KI-vec versus the table last column with blue, I don't know, with line width 2. Since I've increased the KI vector range, it might take a little bit to calculate that. We are roughly using 1,000 points, I guess, here. But we'll see. Ideally, what you have to do is you have to come up with a huge interval and look for a local optima and then just get closer to that. But yeah, let's see. Seems like yeah. So we could start from 20 and we could then look up towards the other part, but it seems like we have a slight issue here. Let us go to linspace and use maybe 50 points in order to see what's going on here. So the first part was, of course, not very good, but we can see that as the KI value increases, we get better results. So we should choose a huge number, I guess. Seems like here we will have 38. So let us try, for example, 200 and 300, or maybe even 1,000, maybe. Let's have it 100. Yeah, it seems like it will go upwards from there. So our ideal interval is 140 and actually 100. So 20 to 140. Let's see. Of course, I'm just using 50 points. I should have a higher grid. There we see we have kind of this interval here. And yeah, the minimum value, of course, between 100 and 120 seems to be like it. So let's have 100 and 120 with 500 points. So hopefully it will solve it. There we go. Now we have this kind of solution here. But it seems like the objective does not go under 38 roughly. So this is the best we can get for now, seems like it. So let's actually choose that solution. Val and index. Let's have the minimum of the table's last column. Let's also maybe plot it because we can. Ki vec index val. So then we know what the index is. We can just get the optimal row. So table, index, get everything here. And of course, the first value is KD, KP, and KI. So what I can do is I can just use TF row. The first three parameters are the controller parameters. I've especially chosen them like that. So let's get all the data here. Let's get the step info. And then let's also have the step response. X label is KI. Y label is objective. Title optimization. Second one, X label, time, title, step response. So this is more about the optimization. And then here we will plot T comma Y, line with 2. Yeah, maybe we can also have a little display name here. And that would be the following: TS plus string info.settling time. And then also the overshoot value, maybe string info.overshoot. Yeah. So let's run this. Yeah. Now, where's our legend actually? Display name ax2.show maybe. Let's also, oh, maybe hold on and grid on. No, it should change. There we go. Now, we can see that the optimal KI value seems to be around 107 or 8. And then we have our settling time, which is exactly 2 seconds. Our overshoot is, of course, not 10% in this case. It seems like it's a low value, but it is not 10%. We didn't expect to have overshoot equals 2. What we can do is maybe we can force to have a better overshoot by just increasing the importance of the second one. Of course, we have a very narrow interval, but let's try it out if it's going to make sense. By the way, I did not reduce this. This should always add up to 1. So this would be better. Let's see if it's going to choose a better overshoot value. 245 was the last one. Yeah, it increased it just a little bit to 60 by just giving up on the settling time. And it seems like the value should be more to the left. So let me just give 0 instead of 120. Maybe it wants to return to the left. Maybe there's a better solution on the left side. Let's see. But you can see the point. It gets us to the settling time, but the overshoot value was not satisfactory. In this case, it just actually screwed up as far as I can see. And the reason for that is it came up with a solution, but now everything is inverse. So we have a negative sign and it's quite on the edge here. So it's not really what we might want to choose because it's fairly close to 0. So ZBK FS in order to see what it is. In fact, it has a pole 0 cancellation and it has it did come up with a PD controller that has a right half plane 0, which is very interesting. We are not looking for that, so I'm going to. But you did see that it just came up with a better solution in terms of overshoot and settling time. But I'm going to stick with this solution. At least it's a PID controller. I didn't check it out, but I was almost sure that it was a PID. And of course, it's way better than having this response here. So if we just blindly look at the overshoots and settling time values, it seems like we can only get this as a response, which also looks awkward, by the way. If you would have been in a car or in a plane that has this acceleration path, it would be very weird to travel on something like this because you would just have a high impact velocity increase and then it would just go easy on you a little bit. In fact, it will fall back and then it would just increase slowly again. So it has a weird shape in terms of control, in terms of behavior. So this brings up, and I told you that this is a terrifying problem that we're addressing today, because we have used the tabulation method, which is seemingly the method that should solve everything here. But it seems like we're stuck somewhere because, yeah, this shape is not ideal. We didn't meet the overshoot requirements. And yeah, even though we have the settling time, it doesn't really matter. The shape does not look right. So yeah, what can we do? How can we propose a PID controller that obviously will work better than this? So the idea here is the following. First of all, let's look at the controller. Yeah, we have this PID controller, and we have this system here. And if we look at the pole 0 map, let me just quickly add a pole 0 map to it. Hold on, grid on, sigma, y label should be j omega. We should call it a pole 0 map, x3. So, poles, PZ map, plot x3, the real values of poles, imaginary value of poles, and then same goes for the zeros. I can also have an S grid in terms of grid on. I can just get rid of grid on here real quick. Since we know what the zeta values are, zeta and omega n, so we can show the dominant poles. So now it seems like we have, first of all, two zeros that are even more dominant than our poles. Our third pole is far away, which is nice, but our pole pair is here, which are also not far away from the zeros. But yeah, this is not an ideal. We are not at an ideal position. We can see that we are on the omega n circle on the zeta line. We have pretty much calculated everything as it should be, but our zeros are dominant, and then we have this weird behavior. Now, yeah, so how can we propose a PID controller that works better than this? Now, the idea is the following. We have actually something, we have talked about something called pole zero cancellation. And last week we have tried to cancel poles and zeros, and it was in fact one of the best solutions that we could acquire, but then the controller was not a PI controller, I guess, as far as I remember, something like that. So what if we would have tried to cancel poles with our controller zeros? So what would be the outcome of that? Now, for proposing a PID controller, what we can do is we can just choose both of these poles as the zeros of the PID controller, because we have two zeros in our PID controller, and we can get rid of these two. And then we would end up in just one pole, and it would end up in something quite interesting. So Q2. What if our PID controller looks like this? So what was the polynomial here? Let's just take this. And then 1, 0. The only thing that would be left is basically the coefficient k. So what I can do is I can look at fs times gs, and then open up a figure, and then plot the root locus. And then look at the root locus of this. Because what I have done right now is the following. I have taken the zero polynomial on top of the pole polynomial, so they will cancel each other out. And I have added just one integrator, or one pole at the origin. Now, this is kind of a pole zero approach, so I can quickly look at the root locus and try to come up with reasoning about this, or I can just foresee what's going to happen if I change the parameter k, because I have already decided on the zeros of the PID controller, and there's the inevitable fact that I am going to add a pole at the origin. So there's nothing left than just having a gain here. So I have pretty much calculated everything by pole zero cancellation. The only thing is that I'm basically trying to come up with a p-type controller, because I have already chosen the zeros. There are many perspectives in controller design that we can choose from. And one of them is the algebraic method, where we have just coefficients, and then we try this tabulation method, etc. But then there's this root locus method, where if we use pole zero cancellation, we have already decided on the dynamic parts of our controller. Then there we are left with the p-type controller, which is a static gain. So we know already how to handle this. So we can look at the problem here. I have added the zeta omega n because that's our desired point. That's our point where we want to assign our dominant poles in order to match the setting time and overshoot values. So let's see what we are going to get from this, out of this. So it still works. So now we can see actually in the previous design, we had almost a pole zero cancellation. So it is kind of interesting that we tried it directly because they could have been on top of each other. And this is the case when that happens. Now, the difference between the figure 1 pole zero map and the root locus plot that I'm looking at is the following. Of course, it's not possible to get the desired poles here like this, but it is also not possible to get them dominant. These seem to be the poles of the closed loop, but they're not dominant. So this is also worth nothing. And here we can also not reach them. So this is also worth nothing. So they are not that different from each other because both solutions do not give the desired results. In fact, if I choose something like this, something around here somewhere on the settling time line here, I almost did get it, like this, I would end up in the exact settling time that I'm after, but I would get overshoot 0. And here I have settling time equals 2, and overshoot is 2.45, which is not basically that off. But at least by choosing to cancel poles and zeros, what I would get is I would get at least a good behavior out of the shape here. It would not just accelerate, slow down, accelerate again. Instead, it would just have a smooth transitioning in terms of shape. And the gain here seems to be equal to 2. So the PID controller can be chosen like 2 times this. And of course, I can then calculate everything that I've done so far. So let me just this here, and let me just attach Q2 here. And yeah, maybe we should also do this here. With thread. There we go. So now we can see the difference here. Instead of having this weird behavior, as I've told you, we have this nice, smooth behavior. At least we don't waste our energy here. And here, maybe we're just slowly rising up to the input here. But of course, we can see that the overshoot is exactly 0. And we have a pole 0 cancellation here. And then we have a pole which would be on the settling timeline here. So they share the real part here. Zeta times omega n is basically the value here, the real value here. So that is it. Now, we would propose this PID controller 2 times this instead of having the previous one, which I didn't write down, but you get the point. So what about C? So we have proposed a pole 0 cancellation PID controller, but we can see where we can improve here on this controller. And we're not restricted on the PID controller. This means that we can alter its structure a little bit. Now, the only thing missing here that if we would add to this system or to this root locus is to be able to assign a certain zeta value. So we need to add just one pole, and we can also determine on how to add that so that we go through this design point here. I would rather have another pole and have them intersect somewhere here, because if I have two poles, due to pole zero cancellation, they would just go to up to infinity and to minus infinity, down to minus infinity. I should choose the position of the next pole that I'm going to add to the controller wisely, so that the intersection point will happen at -2. One will go up, the other will go down, and I can choose the p-type controller accordingly to assign the desired behavior. Now, since I have one at the origin, and since my aim is to get -2 here, I would add the next pole at -4. And the reason would be basically the intersection point would be at half, so at -2. So instead of doing this, let me change the controller a little bit. A PID controller is not sufficient. But what I can do is I can just add one more pole to it. At 4, s plus 4. And if I don't want to mess up the coefficients, the gain of the controller, I can just normalize it. So 4 divided by s plus 4 doesn't change basically the gain of the PID controller. So if I add this and look at the root locus, let me just comment out everything else and create another figure here. Let's see what happens. Now there we go. This is exactly what I've talked about. They are intersecting at -2 due to the settling time. I need 2 because 4 divided by 2 gives 2 seconds. And if I choose the gain correctly, it should assign it to the zeta value that I want to get. And I'm not quite sure, but it should be around 284, 294, 2.9 maybe. Let's choose 2.9. 2.9 times. Of course, you can directly calculate this value. Maybe it's 285, I don't know. So let's open up this one. Let's assign it a magenta color. Let's call it Q3. Again, it's in magenta color. And we should be good to go. There we go. Now let's change this a little bit. Now we can see that our overshoot value is 10.22 something, and we have settling time 1.73 something. We have the desired overshoot, we have a pole zero cancellation here, and we have our desired characteristic polynomial, or the desired poles, and they are indeed dominant due to the pole zero cancellation that we have. So we have kind of changed the PID controller into a pre-filter, or a filter times a first order filter times PID controller in order to get the result out of our design. So now actually this pole zero cancellation here is a specific filter. Now we didn't look at the open loop step response of the actual system, but what we will see is that there's a strange behaving system that we're trying to control here. Let me just get the step response of GS and plot t comma y with k, line width 2. Of course, a new figure, let's call it 4. So let's run this piece of code here. Let's open up 4. There you can see that the system has actually high oscillations, a high frequency mode in it. And we can also see that the roots of this is not arbitrary. You can see that we have a imaginary part of 5. And if you solve it for 2 times zeta omega n and omega n squared is basically 25.01. And then from here, I can see omega n is basically 5.1. And if this is equal to 0.2 here, so zeta should be 0.1 divided by 5.1 here, which is 0.01. So zeta is 0.01, if I'm not wrong. So if you look at the system, the damping ratio is almost 0. So it is very, very low. And we have a high frequency value, omega n is equal to 5. So we have this behavior here. Now, if we are adding a set of zeros in order to cancel this pole pair out, what we're designing is basically we're designing a notch filter, which is basically a bandstop filter, and the frequency of the bandstop filter is basically 5.1 or around 5.1. So what the internals of the controller has, it has a bandstop filter because the system has a very bad behavior at this frequency, so we're suppressing that. And since we are interested in low frequency, we are designing a controller for step response, which means low frequency. We are basically adding a bandstop filter by canceling out the zeros here or placing them near a cancellation. Then we get the notch filter plus some dynamics in order to get the result that we want. So basically, this is a well-known thing called the notch filter, but it is also very dangerous in terms of modeling errors, because you can see that the zeta value is so low that we are actually somewhere around the imaginary axis here. And if I, for example, since we are using GS all of the time, if I, for example, change GS a little bit, if I add some errors to it, let's say the coefficient is 0.25, and then we have 24 here. So let me just try to run everything. So you can see that all the graphics did change. You can see that we have some high frequency components in our step responses here. So let me just show you there. So we can, of course, you can see the setting time values did change, of course, but yeah, we're still lucky that our system is basically stable, because it could happen that we might miss the point. So let me try to do that. Maybe we should decrease it a little bit. Let's see what happens. So if the notch filter is not designed very well, if the pole zero cancellation does not really happen perfectly, then we will have some high frequency components in our step response, and we'll see some issues. Again, we can still see the high frequency effects. I am just changing the position as a little bit, but yeah, I didn't still come up with a a solution that ends up being unstable. So let me try again. There should be a value, but I'm not good at picking values, seems like it. So let us try again. Yeah, there we go. Since we are close to the j omega axis, there's a possibility that we might end up in unstable behavior because we are passing the j omega axis. It creates a little, as you can see here, it creates a little path on the j omega axis. It is crossing it basically, and if you are not careful, if you didn't model it well, if you don't have a good model at hand, you might end up in this position and you might end up in instability. But if it's not that dramatic, as you can see, if it's, for example, something like this, it still works, but the notch filter is not able to suppress all the high frequency elements of the system, and you might end up in high frequency components. As you can see here, we have still some high frequency components. Even though we've designed our notch filter, we have we couldn't get rid of the high frequency effects here. But if the model is perfect, if we are having the exact the model that we assume, then we will get the following result. There we go. Now it seems like as a control system designer, sometimes knowing the system or knowing specifics about the system might help out in coming up with better designs. And sometimes the controller structure is not ideal for your system. In this case, you need some knowledge or you need some perspective on your system so that you can improve on that. And sometimes root locus is the way to go in order to assume certain stuff. For example, we've seen that using numerical optimization, we end up in a almost pole zero cancellation, but since we are forcing the dominant poles to be on a specific point location, it tried to come up with the best solution it could, but it didn't work out for us because we had this strange behavior. But if we examine the pole zero map, we've seen that there might be a pole zero cancellation. If that's happening, we would have a third pole on the real axis. So we tried to cancel the pole zero out. Then we had this red design here, but then we've seen and recognized that the overshoot value is causing us a problem. Since we're on the real axis, it's not possible to get overshoot. So we added another pole, and we knew exactly where to add it because we knew that we have a settling timeline to be on. So we knew that the real part should be -2. If we have two poles, they will intersect at the middle. So if we add it at -4, they will intersect at -2. So we would then choose the according p-type controller that will assign the zeta value that we're after. Then we ended up in this magenta color here. So what about model matching controller, or the controller using the model matching method? Let's come up with a controller to use the model matching method. Well, the name model matching is quite important here to note. And most of the time during the, is it now Q4? Yeah, Q4. So model matching controller. So most of the time when we design a controller, you can also look up here. What we do is we do the following. We assume the structure of the controller. Then we have the system. We look at the closed loop transfer function, look at the pole zeros, look at the dominance factor, etc. But what if we would attack the problem from a different angle? What if we assume that we have a closed loop transfer function that we want to achieve? In our case, luckily, we have something like that. Ideally, we would have to We would like to have zeta and omega n values here, and this desired polynomial here. So if you look close to this desired polynomial here, you would see that this should be the characteristic polynomial of a, let's say, transfer function. If the closed loop transfer function looks like the desired polynomial, then we would be happy. Of course, we would not be entirely happy with this transfer function choice, because if you look at the final value theorem, if you plug in s equals 0, these terms vanish, and we will end up getting a DC gain of 1 divided by omega n squared. So if we add omega n squared here, the DC gain, or the steady state value of the transfer function, would be equal 1. So that would be the ideal transfer function here. So what if we want to choose this as a closed loop transfer function, but are looking for the controller that will give us exactly this closed loop transfer function? So most of the time we have a PID controller, PI controller, whatsoever. We have a structure in our mind, and we try to design the closed loop accordingly so that we get the best dominance factor, etc., etc. But here we don't do that. We don't assume anything about the controller. We let it free, but we fix the closed loop that we should end up in. So we're choosing TDS, not PDS, not the characteristic polynomial, not some part of the characteristic polynomial, but the entire closed loop transfer function. So this is a whole different topic here, whole different thing, but the only thing that will not change is the structure. We will still have fs times gs divided by 1 plus fs times gs, and that should theoretically be equal to TDS. So we're after a controller that satisfies this. Two restrictions. One of them is TDS. It should be exactly like this. And the other one is that we should use a feedback loop. So we're looking for a controller, as usual, that is placed in this loop. Nothing new. But the problem is we don't know what the structure is, what the coefficients are going to be. So how can we come up with a controller if we're using this method here? So basically we need to work around this equation here. We're using the structure to our advantage. Now, if I multiply with this term, I'll get fsgs, fs times gs equals TDS times this. Now, from here on, I will just distribute this. There we go. Now, I know what GS is. I know what TDS is. I'm interested in FS. So I should leave FS and factor it out somehow, like this. And on the right-hand side, I can see that we have GS. So I can just do something like this here. And yeah, I can also see that I could do something like FS times 1 minus TDS times GS equals TDS. We are in SISO, so it's not important. The ordering is not important here. If we were in MIMO, this would be terribly wrong, I guess. But in SISO, we're okay. So now what we can do is we can factor out, or we can just send this part to the other side so that we end up in 1 minus TDS. So if I want to move from 131 to 132 by taking the inverse of the system, so it would look like this, GS times this, I need to assume that GS is invertible, and the inverse of GS, so 1 divided by GS, is stable. Because I'm taking the inverse and I want to have some internal stability in my whole structure. By the way, we have stability from input to output, which is basically the stability of the closed loop transfer function, TDS in this case. That's called stability. but it is just the stability between input and output. If we are talking about internal stability, what we're talking about the stability between any 2 points on the whole structure here. So it could be the transfer function fs, it could be the transfer function gs, it could be the transfer function fs times gs, it could be the transfer function 1 divided by 1 plus fs gs, or anything else. Any transfer function that I can write from the structure should be stable if I want to call the system internally stable. So therefore, if I want to have internal stability, I need to have a stable system. So if GS is unstable, I am not going to use this method at all, because the inverse would not be stable. Or if it is basically minimum real, so minimum, if it's a minimum phase system, that's what I'm actually looking for here. And the reason why we need minimum phase systems is that the inverse should be stable, GS should be stable, so everything should be on the left half plane. Because if we have, for example, s minus 1 divided by something like s squared plus 2s plus 2, let's say, if this is our transfer function, here, if this is our transfer function, the inverse would be this one here. And you can see the inverse is not stable. So all the zeros and all the poles of a system should be in the left half plane if you want to have a minimum phase system. If something is on the right half plane, you don't have a minimum phase system. If it's a pole, if it's a zero, doesn't matter. Therefore, if we define minimum phase systems, we define it as the system and its inverse should be stable. This is basically another way of saying that all the poles and zeros should be on the left half plane. It's basically the same. This has never been an issue for us, so therefore I'm just saying this, but it's not going to be a problem in the usual sense, because we are most of the time working with minimum phase systems up to this point. So if GS is invertible and if the inverse is stable, then we will end up in something like this. And voila, you have actually an equation that gives you a controller directly without doing anything. You didn't even design a controller. The controller depends on the desired closed loop transfer function TDS and GS itself, and in fact it depends on the inverse of GS, and that's it. You need GS, which is going to be your transfer function, and you need a desired closed loop transfer function. You can use these two in order to come up with a controller. Now, if you look close to this here, yeah, let's say we have LS, a loop transfer function here. And let's calculate the closed loop here. So the closed loop of this would be LSD divided by 1 plus LSD. Now, if we work this out, you would see that we get this here. We want to see what LSD is, so therefore this goes to the left. And if you factor it out, it would be 1 minus t times this here, and therefore this would look like t divided by 1 minus t. So basically I can also yes, actually, yeah. So this is basically LDS, TDS, and TDS. You can recognize that TDS divided by 1 minus TDS appears here. So therefore, I could say that this is basically LDS divided by GS. Because LDS is TDS divided by 1 minus TDS. So if I divide that by GS, I will get the controller. And I can also see that FS times GS is basically LDS. So this is actually something that we already know. There's a method called control with the inverse of a system, which is an open loop control strategy. And this is exactly the aim that we have there. But here we have it as a closed loop structure. So what we're basically doing is we're getting rid of unnecessary stuff. There's a pole zero cancellation here if you look close here, because let me get rid of everything here. We have the inverse of the system, which means that, for example, s plus 1 divided by s plus 2. Let's say this is our system. The inverse of the system and multiplying with the inverse of the system means that we will multiply with this. So we're canceling the poles and zeros of the system because we're multiplying it with the inverse. And then we place some poles, some desired poles to the loop structure here. And this is going to be our controller. So it is interesting, and I'm going to show you that basically for our design here, let's design the controller. Let me just get rid of extra spaces here. So if I want to design a controller, what I can do is I can just use feedback here. And yeah, let me just directly use this here for the sake of simplicity. But first I have to define TDS. And TDS is basically omega n squared divided by 1, 2 times zeta times omega n, and omega n squared. Because we are looking for the desired polynomial, and we're making a transfer function out of it. And we can do it by just using omega n squared as the numerator, and then PDS as the denominator for DC gain 1. So then I can just directly use this here. But the problem here would be that I would end up in the following. FS, and it seems like it's a fourth order controller with some poles and zeros. But if you look at ZBK of FS, so let us see. You can see that there's actually an internal cancellation here. There we go, s squared plus 4s plus 1145. They appear on the numerator and denominator. So what we can do is we can just use min real in order to get rid of the cancellations. Then we could look at ZBK. There we go. We have s squared plus 0.2s plus 2501 divided by s plus s s times s plus 4, and our coefficient is 11.446. Now, this gives us directly the controller because we are basically canceling the system out. This is the inverse of the system, therefore we have that part. But s and s plus 4 is basically LDS, because we can look at LDS is min real TDS divided by 1 minus TDS. Now you could see that this is basically the loop transfer function, the ideal loop transfer function that we're looking at. And we're adding basically the inverse of the system to it. So LDS divided by GS will give us basically the same. Here, this is basically FS. So we come up with an ideal loop transfer function, which is basically coming from TDS. If this would have been an open loop transfer function, then we would have chosen 1145 divided by s squared plus 4s. If you take the closed loop of this, you will get TDS. So, well, this is called the model matching controller, and the reason for that is that it uses the system's inverse because it is matching the zeros with poles and the poles with zeros. Therefore, it is called model matching controller, and as you might suspect from the name, if the model is not correct, your controller will mess up. So this is a strategy based on pole zero cancellation, and this is the most general form of pole zero cancellation because last week and this week we have talked about pole zero cancellation. The controller that does this, the method that does this is model matching controller. And you are getting rid of all the poles and zeros in this case. This is the most general form, therefore. You get rid of all the poles and zeros by just taking the inverse as a part of the controller. So the controller itself has the system dynamics. So it's matching the controller, it's getting rid of the controller, and then it's adding the necessary stuff that is to achieve TDS. So it's a very basic and very easy controller and controller design method because you have to come up with a desired closed loop transfer function. Then you can use this identity and main real, and you're good to go. We design a controller in just basically 2 steps. If you just place this into the main real, we have just used 2 steps here, not more. Now, the interesting part is the following. Actually, in the previous question, today, we have chosen in B, in the second one here, propose a PID controller. We have chosen something like this, which had already this numerator here. You can see that we had already this part here. And then we had also this integrator. So we have actually used these 2 parts here and the gain 2 as I'm concerned, yep, in order to try to come up with a controller. Then in Q3, we basically updated our choice and we talked about the fact that we need to add S+4. So we basically included this part too. And due to S+4, due to the change of gain, we also added 4 here and we have 2.9. So 2.9 times 4, which was not the perfect one, but it was approximately 11.6. So if you look close to this controller, we have basically the same controller. So in C, where we propose a controller, we were actually proposing the model matching method controller. So the model matching controller. And this basically gives us a hint and says that if you are trying to design a controller, you might need to consider model matching controller in order to get a rough idea what the most general and form of your controller could look like. And in this case, a PID was not sufficient due to the fact that the system had a real pole during after the cancellation, and we couldn't generate this overshoot. So we needed to add another pole in order to get some complex conjugate pairs out of it in order to get our desired specifications in order to meet them. So the model matching controller can give you a rough idea on what the controller structure should look like. Then you could come up with a controller, and yeah, otherwise you might have a PID controller, but we're not really sure if this PID controller is going to be sufficient. In this case, there's also this notch filter part. So sometimes it is important to look at the model matching controller. For some systems, this might work very well. For some systems, this might be an overkill. So it depends on the system, on the system. But for our today's discussion, the system was chosen specifically, and using a tabulation method, we didn't come up with the best solution because the structure was insufficient. If we would have just updated our control structure up here, if we would add another unknown, let's add a filter, for example, if I would say, okay, let's add some V and let's multiply FSS with, I don't know, V divided by S plus V, something like this, then I could end up in the same solution. But this is not a PID controller. So it tries to make the point that PID controller might not be sufficient for all your specifications. Choosing these specifications is also an important topic, but here we are given 2 specifications and the PID controller is not able to match that. But with a little alteration, with a little change in the PID structure or in the design choice, we can cancel it out. We come up with a notch filter. Due to the notch filter, due to the high frequency, low damping poles, we needed to come up with a notch filter. When we do that, we see that that's not sufficient because we need another pole, we need an extra pole in order to get some complex conjugate pair out of it. We proposed a controller like that, and it ended up being the model matching controller. So that's basically what we have done today. So you can just check out the PDF here. You will see that I also use some methods out of your lecture notes where you can just use the matrix notation in order to design or come up with the set of equations here. You can do it manually. You can use this matrix method, whichever you want, but sometimes having a change in the documentation is nice. So you can see that there's this tabulation stuff, and then we ended up in this strange behavior. Now, we propose to cancel out the poles and zeros, and this was roughly our transfer function. You can see there's an almost cancellation, and if it's perfect, it would be 2 divided by s plus 2, the closed loop here. And we added another pole so that we end up in overshoot, as you can see here. Then the model matching controller ended up being the same. So having a bit of that and a bit of this is important. So check out on, if you're trying to design a control loop, look at the PID controller. Maybe you need a model matching controller. It depends on the application. But you can see that we are actually designing model matching controllers all along, last week and this week, because pole zero cancellation is kind of model matching controller. The difference would be to have a partial model matching controller, because if you don't cancel everything out, then you're not matching the whole model, but you're partially matching it. But other than that, what I can say is I can say the following: using the tabulation method, using the algebraic method is important, but you have to attack the problem from different angles. And a combination of the algebraic method and the root locus method would help you out more than sticking to just one of them. So this is basically it for this week. And next week, we don't have a laboratory session at all, because next week we have the off week. Then you will have an exam. So I would highly recommend you to check out the lecture notes that I provide you. But remember that these questions are designed for MATLAB solving. So you need to use pen and paper and study a little bit that way, because you will have a classical exam. You will not have MATLAB or nothing else. I will upload some playlists in Turkish and in English as soon as possible. So you can just watch them and try my exercises along with my videos. And yeah, that's basically it. This is basically it for this week. I would probably show up in your exam too, but see you at the exam then. If you have any questions, feel free to ask, but if not, good luck in the exam.